Hello and welcome to the world of Kubernetes. My name is Udesh Kumar and I'll be your instructor for this course. In this course, you'll be learning about the foundations of Kubernetes, setting up a Kubernetes cluster, writing Kubernetes configuration files in YAML, setting up Kubernetes components like replica sets, deployments, pods, and services. And we'll also look at deploying applications on Kubernetes. This course is intended for anybody who wants to begin their career in DevOps and to start learning with Kubernetes. We'll also learn about Kubernetes architecture, the core components of Kubernetes, and how to deploy, manage, and scale Kubernetes applications. This course also contains several hands-on demo videos that will show you how Kubernetes works in the real-world scenario. There are also quizzes which you can attempt to validate your knowledge. Whether you are a developer, a student, or even a technical manager, this course is perfectly designed for you to understand every single aspect on Kubernetes at a foundational level. I hope you find this course helpful. All the best, and we'll see in the end of the course. So overall, through the course, we'll be going through what are containers, what is container orchestration, why do we need container orchestration, then introduction to Kubernetes, its features, benefits, how the architecture of Kubernetes looks like, how Kubernetes can be set up, and followed by a demo. And then we'll be discussing about the components in Kubernetes, such as pods, pods with YAML files, replication controllers, replica sets, deployments, and updating and rollback of deployments. And we'll also have demo for each of those. And then we'll discuss about networking in Kubernetes and how services are implemented on Kubernetes. We'll also take a look at how the microservices architecture looks like, and we'll also see how we can deploy an application on pods and deployments. We'll also discuss about Google's Kubernetes offering, Google Kubernetes Engine, alias GKE. With that being said, let's move into the course. Now, let's get introduced to containers. So, what are containers? Briefly talking, containers are a way to package software and its dependencies into a single unit which can be used to run across multiple environments consistently. So how can we do that? So first, let's understand the difference between virtual machines and containers. So what is a virtual machine? It is a virtualized infrastructure where you can manage the servers by your own. And now what are containers? So to find the difference or to understand the difference, consider a desktop and a laptop. On a desktop, you have a CPU, which is basically the server. And for using that CPU, you need a desktop monitor, a keyboard, a mouse, maybe speakers. So all of these components becomes a dependency to use that CPU. Similarly, look at laptops. It comes with an inbuilt screen, it comes with an inbuilt keyboard, it has a trackpad with it. So all the dependencies that we mentioned on the desktop comes along in laptop. So it is packaged as a single unit, and you can carry laptops everywhere. Similarly, desktops are like virtual machines. If you have an application, you need to install dependencies by yourself, and you have to manage it, you have to upgrade it, and you basically have to look for its entire lifecycle. So when it comes to containers, you can create a container image with the application code and its dependencies built together into a single unit. Once you have a container image, that one container image can be used to run multiple containers. It is very lightweight because it's just one image, and it is also portable, and these containers will encapsulate all the application and its runtime environment. So if you look at the diagram here on the right side, you first have an infrastructure,
On top of that, you have the operating system. And on top of the operating system is where you run containers. And to run containers, you need a container runtime. So here we are using a container runtime called Docker. So Docker is the container runtime that manages all the containers running inside it. And if you look at app A, app B, app C until F, all of these are containers. So app A is a container, it has an application and its dependencies. App B is similarly another application with its dependencies. And likewise goes app C, D, E, and F. And Docker is responsible for managing all of these containers. So it can run on any machine that supports the container runtime, regardless of any hardware or operating system. So for example, if you have a Windows server or if you have a Linux operating system, it will still run because Docker supports all of these. And another example apart from Docker is Podman. What is container orchestration? How can we orchestrate these containers better? What is container orchestration in general? It is the process of automating the deployment, scaling, and management of these containerized applications. For example, we had the Docker container. How can we automate the deployment of a Docker container? How can we scale the Docker containers? Or how can we manage the containers? The process is known as container orchestration. So a container orchestrator allows the management of a large number of containers across multiple hosts while ensuring high availability and scalability. And what is high availability? It means it will scale itself to make the application available for all the users using that application. And it also provides a way to define, deploy, and manage the containerized application as a whole rather than the individual containers. For example, let's say you have 5 containers, and managing 5 containers might be quite somewhat an average job. But when it comes to 1,000 containers, managing 1,000 containers is going to be a tedious task. And you want to find a way to automate all this. And that is where container orchestration comes in. A container orchestrator will manage all the containers running inside it. So the best examples are Kubernetes, the best in the market, and what we are going to discuss in the upcoming lectures. And then we also have Docker Swarm, which is a native container orchestrator for Docker containers. And then we also have Mesois, and there are a lot of others also. But in this course, we will be focusing on Kubernetes. Welcome to the lecture Introduction to Kubernetes. Kubernetes is an open source container orchestration platform that automates the deployment, scaling, and management of containerized applications. It's an open source container orchestration platform which was originally developed by Google and is now maintained by Cloud Native Computing Foundation, CNCF. Containers are a lightweight way to package software, making it easier to deploy and run applications consistently across multiple environments. However, managing these containers at scale can be challenging. This is where Kubernetes comes in. It provides a platform to manage containerized applications, abstracting away the underlying infrastructure and making it easier to manage and scale applications. It comes with a master slave model where the master node controls the cluster and is also responsible for making decisions about where to deploy applications. The worker nodes run the containers and execute the workloads. Kubernetes also provides a declarative approach to managing infrastructure where you specify the desired state of the application and Kubernetes takes care of making it happen. And when we look at the master node components, it includes API server, HCD, scheduler, and control manager. And the worker nodes will contain container runtime such as Docker or Podman, and the Kubernetes agent known as kubelet. And kubelet is responsible for communication between master and worker nodes. So, in summary, Kubernetes is an essential tool for managing containerized application at scale, and it is also used by a lot of organizations around the world. So, whether you are on a small project or a large application, Kubernetes helps you manage your infrastructure more efficiently and effectively. Now, let's look at the features and benefits offered by Kubernetes. Let's take a look at the benefits of Kubernetes first. Kubernetes provides a lot of benefits to the organization managing these containerized applications at scale. So, some of the key benefits are scalability, portability, resource efficiency, automation, and availability. Kubernetes can scale applications up or down based on demand automatically. And this ensures that your application is always available and performing optimally. And this helps in reducing the cost and complexity of managing the infrastructure. Next comes portability. Kubernetes provides a platform for running applications consistently across different environments, and it makes it easier to move workloads between on-premises data centers and cloud providers. And the third one is resource efficiency. It enables the efficient use of resources and thus increases the utilization of all the resources. And it automate tasks, reducing the manual intervention, and it improves the operational efficiency overall. And it also makes sure that it is highly available and reliable for your applications, thus reducing these downtime and ensuring business continuity. Apart from these, Kubernetes is also flexible as it provides a modular architecture that can be customized and extended to meet the specific needs of your organization. It supports a wide range of container runtimes like Docker, Containerd, Podman, Cryo, etc. And Kubernetes is also designed to be highly available and fault tolerant with built-in features like automated failover and self-healing capabilities. And it also gives a declarative approach to managing infrastructure where you can specify the desired state of the application and Kubernetes will take care of it. Now let's look at the features offered by Kubernetes. Kubernetes supports rolling updates and rollbacks, and this allows you to deploy new versions of your application without downtime or disruption to users. And you can quickly roll back if there are any issues. The next one is self-healing. Kubernetes automatically monitors the health of containers and can restart or replace them if they fail or become unresponsive. And this helps us in ensuring that the application is always available and performing well. And Kubernetes is cloud agnostic, so it can run on any cloud provider, on premises, or even hybrid cloud environments. It is designed in such a way that you can run it across variety of cloud platforms or data centers, and you can easily manage and deploy applications across multiple clouds. And Kubernetes also allows in resource management, and you can specify resource requirements for containers and actually schedule them to run on certain nodes. And this helps in optimizing the resource utilization and ensures that your application is running efficiently, and it will also reduce the cost. So Kubernetes also has a built-in service discovery and load balancing mechanism that allows the containers to communicate with each other and ensure that traffic is distributed evenly across each application. So, in summary, Kubernetes provides a powerful platform for managing containerized application with a rich set of features like automation, scalability, resilience, availability, and portability. Now, let's take a look at the architecture of Kubernetes. So, Kubernetes consists of a lot of components, mainly Kube API server, Kube scheduler, Kube controller manager, etcd, kubelet, and Kube proxy. So, it is distributed across the master node or the control plane and the worker nodes. So, the master node contains Kube API server, Kube controller manager, Kube scheduler, and etcd. We will look into each of these components in detail. And on worker nodes, we have kubelet and kube proxy. So it is in the worker nodes where the workloads are running on pods. And each of these pods runs containers. So all of these together creates the cluster. The first component is Kube API server. So the Kube API server is a very key component of the Kubernetes architecture. It is the central control plane component that exposes the Kubernetes API and processes all RESTful API requests sent to the Kubernetes cluster. The Kubernetes API server will be responsible for serving the Kubernetes API. Kubernetes API, it provides a programmatic interface for managing this cluster. The API is used by various Kubernetes components and external tools to interact within the cluster. Kube API server is also responsible for authenticating and authorizing API requests. So it authenticates and authorizes all the API requests that are sent to the cluster. It uses the Kubernetes authentication and authorization plugins to verify the credentials of the user or application making the request and to ensure that the request is authorized based on the user's role or permission. And it is also responsible for validating and admitting API requests. The Kube API server validates and admits all API requests that are sent to the cluster. It checks that the request is properly formatted and contains all the information. It also runs admission control plugins, which can modify or reject requests based on custom rules and policies. And it is also responsible for managing the state of the cluster, including all configuration of Kubernetes objects such as pods, services, etc. And it stores the state in etcd, which is a distributed key value store that provides a reliable and consistent data store for the cluster. So the Kube API server is designed to be highly available and fault tolerant. It can be run in a clustered configuration with multiple replicas. And it supports various authentication and authorization mechanisms, including client certificates, bearer tokens, and OpenID Connect. So in summary, the Kube API server is a critical component of the Kubernetes architecture. And it provides a central point of control for managing the cluster and ensuring that all API requests are authenticated, authorized, and validated. So it is really important to understand how the Kube API server works for anybody who is looking to deploy and manage Kubernetes clusters. And the next component is Kube scheduler. Kube scheduler is a key component of Kubernetes, and it is responsible for scheduling pods and deployments into nodes in the cluster. It runs as a single process on the master node of the cluster and is responsible for ensuring that the pods are scheduled to run on the most suitable node based on their resource requirements and other constraints. The kube scheduler is responsible for node selection, resource allocation, interpod affinity, node constraints, etc. The kube scheduler selects the most appropriate node to run a pod based on the pod's resource requirements and other constraints such as node affinity or anti-affinity. The kube scheduler ensures that the resources required by a pod, such as CPU and memory, are available on the selected node before scheduling the pod to run. And the kube scheduler also takes into account the affinity and anti-affinity requirements of pods when scheduling them onto the nodes. This ensures that pods that need to be co-located are scheduled on the same node. The kube scheduler also takes into account the constraints on the nodes, such as taints and tolerations, while selecting the nodes to schedule the pods. We will look at taints and tolerations and affinity in a later course, but let's stick to the basics for now. The kube scheduler uses a scheduling algorithm to determine the best node to schedule a pod based on the resource requirements and the constraints of a pod. The scheduling algorithm takes into account a number of factors, including CPU, memory usage of the nodes in the cluster, the storage and the network resources available, and the affinity and anti-affinity requirements of the pods. Once the kube scheduler has selected a node for the pod, it communicates with the kubelet on that node to schedule that pod to run. The kubelet then downloads the container image for the pod and starts the pod's container. So in summary, the kube scheduler is a critical component responsible for scheduling pods into nodes in the cluster. The next component is Kube Controller Manager. Kube Controller Manager is a key component responsible for managing the controllers that regulate the state of the cluster. It again runs as a single process in the master node. It is responsible for ensuring that the desired state of the cluster is maintained. So the Kube Controller Manager has a few controllers within, such as node controller, replica set controller, deployment controller, and stateful set controller. It also has service controller. The node controller is responsible for monitoring the nodes in the cluster and ensuring that the desired state of the nodes is maintained. And this also includes detecting when nodes become unhealthy or unavailable and taking actions to address these issues. Replica set controller is responsible for ensuring that the correct number of replicas of a particular pod is running in the cluster. It monitors the desired state of the replica set and takes action to create or destroy pods as needed to ensure that the desired state is maintained. Deployment controller is responsible for managing the lifecycle of a deployment. It monitors the desired state of the deployment and takes action to create or destroy replica sets and pods as needed to ensure that the desired state is maintained. Stateful set controller is responsible for managing the lifecycle of stateful applications in the cluster. It ensures that the correct number of replicas of a particular stateful application is running in the cluster, and it also takes actions accordingly. Service controller is responsible for ensuring that the correct endpoints are available for services running in the cluster. It monitors the state of the service objects and takes action to update it accordingly. So Kube Controller Manager is responsible for managing the replicas, endpoints, service accounts, and other resources as well. And it mainly ensures the desired state matches the actual state. And you can also extend it for custom controllers. And it is also a very critical component for automation management and ensuring the cluster health. So the Kube Controller Manager works closely with other Kubernetes components such as kubelet and kubeproxy to ensure that the desired state of the cluster is maintained. It communicates with the Kubernetes API server, which is Kube API server, to receive instructions about how to manage the controllers in cluster and reports the status of the controller back to the API server. The next component is etcd. etcd is a distributed key value store that is a critical component of the Kubernetes architecture. It is used by Kubernetes to store and retrieve configuration data and state information. etcd is responsible for maintaining the state of the entire Kubernetes cluster, including information about nodes, pods, services, and other Kubernetes resources. etcd is designed to be highly available and fault tolerant. It uses a distributed consensus algorithm to ensure that the data is replicated across all the nodes in the cluster. And it can survive network partitions and node failures. etcd also supports automatic leader election and automatic data compaction, which helps to ensure that the cluster remains healthy and efficient. Some of the features of etcd includes distributed consensus, which means that it uses a distributed consensus algorithm to ensure that the data is replicated across all the nodes in the cluster. And each node has a consistent view of the cluster's state. And etcd is also designed to be highly available with built-in support for automatic leader election and node failover. etcd is also designed in such a way that if one etcd fails, the other candidates will elect the next leader. And etcd also provides a simple API interface that can be used to store and retrieve configuration data and state information. It also supports a watch API that can be used to monitor changes to the key value store in real time. And it also supports role-based access control, also known as RBAC, and TLS encryption to secure access to the key value store. It is also highly scalable with support for tens of thousands of writes per second. And it is very critical for managing the stateful workloads, also the entire cluster, and ensuring the system's health. The next key component is kubelet. Kubelet is responsible for managing the state of individual nodes in the cluster. It is responsible for starting and stopping containers in a node, and it monitors the Kube API server for changes to desired state of the containers and ensures that the containers are running as expected. It also regularly checks the health of the containers it manages and reports the status of the containers to the Kube API server. If a container is found to be unhealthy, a kubelet can automatically restart or replace the containers. It is also responsible for managing the resources used by the containers on a node, such as CPU, memory, and storage. And it enforces resource constraints specified in the pod manifest and ensures that containers do not exceed their allocated resources. It is also responsible for managing volumes attached to the containers. It mounts volumes specified in the pod manifest and ensures that they are available to the containers. Kubelet also reports the status of the node to the Kubernetes API server. This includes information about the node's available resources, the status of the containers running inside the node, and any events or issues affecting the node. The kubelet runs on each node in the cluster and communicates with the Kube API server to receive instructions about how to manage containers on the node. It works closely with other components such as the kubeproxy and kube controller manager to ensure that the containers are running as expected and the cluster is operating smoothly. And the next component is kube proxy. Kube proxy acts as a network proxy or a load balancer for services running on a Kubernetes cluster. It is responsible for routing traffic to the appropriate pod and container based on the rules defined in the Kubernetes service object. So the kube proxy is responsible for service discovery, load balancing, health checking, and network proxying. So the kube proxy discovers the services running on the Kubernetes cluster and maps them to the IP address of the pods and containers that make up the service. And the kube proxy also load balances the traffic across the pods and containers that make up a service, and it distributes the load evenly, ensuring that each pod receives a fair share of the traffic. And it also regularly health checks the pods and containers that make up a service and remove any that are found to be unhealthy. It also acts as a networking proxy for services running on the cluster, forwarding traffic to the appropriate pod and a container based on the rules defined on kube service. The kube proxy can be run in two different modes. One is user space mode, where kube proxy run as a user space process on each node in the cluster. And it will be responsible for forwarding the traffic to the appropriate pod and container using NAT or Network Address Translator. And the second mode is IP tables mode. And in this mode, kube proxy uses IP tables firewall to forward traffic to the appropriate pod and container. This mode is more efficient than user space mode and is the default mode used by most of the Kubernetes clusters. And it also implements network policies to restrict traffic between pods and services, and is also very essential for ensuring reliable communication between the application. In the upcoming lecture, we will discuss about how we can set up a Kubernetes cluster. Where can we set up Kubernetes clusters? It can be deployed on-premise data centers or in the cloud such as Google Cloud Platform or Amazon Web Services. What are the steps behind it? It involves configuring a cluster of nodes to manage the containers, installing the Kubernetes components, and then deploying the application workloads. In the upcoming demo, we will be looking at how we can create a Kubernetes cluster. So for this demo, I'm going to show you the most simplest way where you can host your Kubernetes cluster in a virtual machine. That is why we are using Minikube. Minikube is a local Kubernetes cluster that makes it easy for you to learn and develop on Kubernetes. For that, all you need is a Docker container or a virtual machine environment. And you can start with a very simple command, minikube start. So what you need for your virtual machine is 2 CPUs or more, and it should have 2 GB of free memory along with 20 GB of disk space. And it should also contain any container or virtual machine manager such as Docker, VirtualBox, Podman, etc. I have a virtual machine with me. I am going to first install Docker. It's on Debian, so I'm going to use the Debian documentation to install Docker. Let's copy the commands. All the older versions are removed. Now let's install using the apt repository. It's done. Let's add the Docker's official JPG key. That's also done. Let's set up the repository. And that's also done. Now let's install Docker engine. So the latest version can be installed using this command. And it's installed. Now let's test if Docker has been installed. Docker has downloaded the image, so it means Docker is working perfectly. Now let's move into installing Minikube. So here I have a Linux machine. So I'm going to use these commands. Installation is done. And now let's start the Minikube cluster. So all the installation that we do for the Kubernetes, Minikube does it for us in a simplified manner. And now you can see that the kubectl is now configured. And if you also observe closely, kubectl is not found. Instead, you need to try minikube kubectl. So let's try this command. And it shows all the pods which are present in this minikube cluster. So minikube kubectl -- this is common with all the commands. So to make our lives easy, I'm going to use alias kubectl equals the command that we copied. So what happened is we assigned this minikube kubectl -- with an alias value of kubectl. This means now instead of running minikube kubectl -- get pods -a, you can just run kubectl get pods -a, and it will work the same. So now you are ready to use your Kubernetes cluster. You can run anything in this one. So that's all about installing Minikube on Kubernetes. In this lecture, we will cover the basics of Kubernetes components and their functionalities at a high level. Specifically, we'll be discussing about 4 of the main components: pods, replica sets, replication controllers, and deployments. So Kubernetes use a declarative model with YAML manifest to define application components. Let's begin with pods. Pods are the smallest deployable unit in Kubernetes, and they represent a single instance of a running process in a cluster. They can contain one or more containers and share the same network namespace, allowing them to communicate with each other using the localhost interface. Pods are designed to be ephemeral, which means they can be created, scaled, and destroyed quickly and easily. Replica sets are responsible for managing a desired number of replicas of a specific pod template. This ensures that a certain number of identical pods are always running in the cluster. If a pod fails, the replica set will automatically create a new one to replace it, maintaining the desired number of replicas. Replication controllers are similar to replica set in that they both ensure that a desired number of replicas of a pod template are running. However, replication controllers are older and have been mostly replaced by replica sets. And then we'll have deployments, which is responsible for managing the deployment and scaling of replica sets. They allow you to declaratively manage your pod replicas, and it can be used to roll out updates or rollbacks to your application with ease. Deployments also provide a declarative updates for pods and replica sets, making it easy to manage the state of your application. And Kubernetes also provides services that provide stable network addressing for pods and load balancing for traffic between them. We'll look into each of these in detail. Pods are the smallest deployable units in Kubernetes, and they represent a single instance of a running process in a cluster. Pods can contain one or more containers and share the same network namespace, and it allows them to communicate with each other using the local host interface. And they are designed to be ephemeral, which means that they can be created, scaled, and destroyed quickly and easily. One of the key features of pods is that they're designed to be isolated from each other. Each pod has its own IP address and its own set of storage volumes. This allows pods to be deployed and managed independently without affecting the rest of the cluster. Typically, pods are used to run a single instance of an application, but they can also be used to run multiple instances of the same application. For example, if you have an application that requires multiple instances for load balancing, you can create multiple pods with the same container image. Pods are also designed to be scalable. You can easily scale the number of replicas of a pod using Kubernetes scaling features. This allows you to increase or decrease the number of running instances of an application depending on the workload. One important thing to note about pod is that they are not designed to be long-lived. When a pod is terminated, all the containers running inside it are terminated as well. This means that any data stored inside the container is lost. To overcome this issue, Kubernetes provides the concept of storage volumes. Storage volumes can be attached to a pod, allowing you to store data even when the pod is terminated. Another feature of pod is that they can be managed using Kubernetes controllers. Kubernetes controllers are responsible for ensuring that the desired number of replicas of a pod are running. This means that if a pod fails, the controller will automatically create a new one to replace it. And thus, it maintains the desired number of replicas. So in summary, pods are the smallest deployable units in Kubernetes, and it is designed to be isolated from each other. It is also designed to be scalable and can be managed using Kubernetes controllers. They can have one or more containers and are designed to be ephemeral, but can be made long-lived by using storage volumes. In the upcoming video, we will see how we can deploy a pod on Kubernetes. So here I have a terminal with me, and I'm going to create pods and manage it using kubectl commands. So first, let's see how many pods are existing. We use the command kubectl get pods. So currently there are no resources in this default namespace. So where does Kubernetes manage all its pods? That is in the kubesystem namespace. How do we know that? That is where we use a namespace kubesystem. And here it is going to give us all the pods it is going to run. And if you look here in the ready status, you'll see 2 by 2, 1 by 1, 4 by 4. So each of those are containers within that pod. And the status of those pods, everything is running and no pods has restarted, and the age from which that pod has been started. We have observed that there is no existing pods in the default namespace. So we are going to create a new pod in that namespace. For that, we have kubectl run followed by the pod name. For this example, I'm going to use nginx, and then we supply the image name, which is again nginx. So we are going to take nginx image and create a pod named nginx. Now let's see if the pod is getting created or not. Now you see that the pod is running. To view the details of the pods, we can use kubectl get pods -o wide, which means it is going to give us all the details: the pod name, the containers, the status, the age, the IP of the pod, and then the node which is running, the readiness gates, and the nominated node. Now, if you want to see a further described details of those pods, you can use kubectl describe pod followed by the pod name. And there you see every information around this pod. So you can see the image ID. Now, if you also want to see it in a YAML file, you can give kubectl get pods -o YAML. And it is going to give you all the details in a YAML format. If you want to write it to a file, then you can use the previous command followed by the text name and it will be written. Let's see the file. And you can see everything is written in that file. Once you have your pod up and running, you'll have some limitations in editing it. You can make changes in this YAML file, but there are several limitations. For example, let's see to change the name of this pod from Nginx to Redis. Now you'll see that the error shows that the API version or the kind or the name was changed. This means you will not be allowed to change any of these. So which is why even if you look at what are the existing pods, you'll still see that the name has not been edited. So to delete it, we can use kubectl delete pod followed by the pod name. And in case if in some places if the pod takes too much time to delete, you can also use --force so that it will be quickly deleted. So that's all about this lecture. We'll see you in the next one. In the previous lecture, we looked at how we can create pods. We haven't discussed how we can use the declarative approach of Kubernetes to create these resources. So that is where we have YAML as a language. So YAML is a markup language that we use to create these resource definitions. So how can we use YAML to create Kubernetes resources? So YAML can be used to define Kubernetes objects like pods. YAML is designed in such a way that it is human readable and the data is in a serialized format. And while mentioning any Kubernetes resources, we need to mention the specifications such as the container image, port, volume, or environment variable. And we should also include metadata such as the name and labels for the pod. You can create a pod by running kubectl apply command with the YAML file as an argument. And you can use kubectl commands to manage and monitor its status, logs, and events. If you look on the right side, you will see a sample format of the pod definition template. So essentially, there are 4 fields present on most of the objects: API version, kind, metadata, and spec. API version is used to specify the version of the Kubernetes API that the object is created with. The version is usually expressed as a string in the format of either group/version or the version alone. Kind is used to specify the type of the object that is being created. For example, here it is pod. We can change it to deployment, stateful set, replica set, storage volume, anything. So the kind field is usually expressed as a string, and the values can be, as I mentioned, deployment, service, pod, replica set, namespace, anything. This is a very important field because it tells Kubernetes how to interpret the object and what kind of behavior should be expected. Metadata is another important field that provides additional information about the object. We have parameters like name, label, and each of those can be passed as a key value pair to the metadata field. For example, if we have a pod, we can mention the pod name in the metadata, and we can apply some labels giving a label parameter and its value to the pod. So this metadata is really important because this allows Kubernetes to manage and organize objects. Spec is used to specify the desired state of the object. It's an object that contains key value pairs that describes the desired state of the object. So here, if you look, we're trying to create a container here in the pod, and the name of the container is busybox, and the container image that we are using is also busybox. So what this template is going to do is that when it is applied, it is going to create a pod with the name pod name and with the label and some label value, and it is going to create a container with the image busybox with the container name busybox. So in the upcoming lecture, we will see how we can use YAML files to create pods. So here I have a YAML file which is currently empty, which is named pod.yaml, and we are going to write the definition file for the pod. So there are 4 components which is critical to a Kubernetes manifest: API version, kind, metadata, and spec. So API version is the version of the Kubernetes API that we are running. Here it is v1. The kind is the type of the resource that we are creating. So here it's pod. And under the metadata is where we give all the details regarding that particular resource or that kind. So the name here is Nginx. And if you also want to apply labels, you can do that. And under the spec, you give the containers. You can give a name to the container, Nginx, and you can specify the image. So once you have the details, you can save it. And this is all you need to create a pod. Now let's go to the terminal and you can use kubectl apply -f pod.yaml. And this YAML file was applied by Kubernetes and the pod is created. Now let's check if the pod has been created or not. Kubectl get pods, Nginx days running. So this is how you can maintain or manage pods using YAML files. And in the upcoming lectures and in hands-on demos, we will see how we can use multiple resources using YAML file. The next components that we are going to discuss are replication controllers and replica sets. They are both responsible for maintaining the desired number of replicas of a specific pod template. This ensures that a certain number of identical pods are always running in the cluster. If a pod fails, the replica set or replication controller will automatically create a new one to replace it and maintains the desired number of replicas. Replication controllers are an older version of replica sets. Replica sets provide more advanced features than replication controllers, such as rolling updates and rollbacks, but both components have the same basic functionality. One of the key features of replication controllers is that it ensures the specific number of replicas of pods that are running. It also provides automatic scaling, self-healing, and fault tolerance features. It also monitors the health of the pods and replaces failed or terminated pods. It can be updated to manage new versions of pods for seamless deployment and is also very critical for managing large-scale containerized applications. So when we look at replica sets, it's almost the same, but replica sets are more advanced. One of the features of replica sets is their ability to perform rolling updates. Rolling updates allow you to update your application without any downtime by creating a new set of pods with the updated version of your application and gradually replacing the old set with a new set. And replica sets can manage stateful or stateless applications, and it also supports rolling updates. It supports complex scaling scenarios based on the resource utilization or based on any specific metrics. And another feature of replica sets is their ability to perform rollbacks like how they perform rolling updates. If an update causes any issues with the application, you can easily roll back to a previous version using the built-in rollback functionality. And replica sets also provide an advanced selector option for targeting pods, which means that you will be able to specify some pods that you want to run. Now let's take a look at the difference between replication controllers and replica sets. So in replication controllers, the selector type is equality based, but in replica set, it is set based, which means that you can select specific pods in replica sets, but in replication controllers, it is equally distributed. In label, when you update it, replication controllers deletes and recreates the pods, which means it is introducing a downtime. But in replica set, it retains the old pods and creates new one before the old ones are deleted, so that the replica sets ensure that there is no downtime. And rolling updates are not supported in replication controllers, whereas in replica set, it is supported for seamless updates. And when you make any changes in pod template, replication controllers, as I mentioned earlier, it deletes and recreates, creating a downtime. But on replica sets, it gradually replaces the older pods, which is similar to the rolling updates. And replication controllers are currently deprecated and is now replaced by replica sets. In this demo, we will be looking into how we can deploy replica sets on Kubernetes. So similar to how we created pods, we can use the same format to create replica sets. So we start with API version, kind, metadata, and spec. So the API version should be apps/v1, because if you look at a pod, then you can give v1, but if you go for a replica set deployment, there you have to be using apps/v1. And then the kind is replica set. And you have to be very sure that the S here is caps. And then in the metadata, you can give the name, let's say demo RS. And you can give a label, app frontend. So app frontend is the label applied to this replica set. And in the spec, we should mention the replicas. Replicas basically means the number of replicas that should be up and running all the time. So replica set will be responsible for making sure that all those 3 replicas here in this case is running all the time. And now once we have the replicas, we have to identify which are the pods associated with this replica sets, because ideally when you look at the architecture diagram, replica sets have pods which is kept up and running all the time. So for that, we need to have a selector under which it should match the labels in the pod. So here I say app frontend. So this is the label. App frontend is the label I have applied to select the pod for this replica set. Now once we have the selector, here is where we need to add the template of the pod. So under the template, we copy all the data under the pod. So we have a pod.yaml file. We copy everything from here and we take it and we paste it here. So now we have a YAML file to create a replica set. And if you need to change the number of replicas, you can change it here. We have copied the previous pods definition, but there is something missing, which is the labels here. So let's add this to the template. So now the replica set YAML file is ready. Let's go to the terminal and create a replica set. Look at the files. Let's use the kubectl command, kubectl apply -f replica set.yaml. And now you see that demo rs is the replica set which is getting created. Now we use kubectl command, kubectl get rs, or you can also use replica sets. And you'll see that the replica set is currently created and the name is here. The desired means the number of pods that should be up and running as we have mentioned in the replicas. And current is the number of running pods which is at the moment running on the replica set. And there are pods which are ready to run, which is currently 3. Now let's see the pods. You see that 3 pods are running, which is the 3 that we have mentioned here. Let's see the details of the replica set using kubectl describe command. So currently you'll see that the name, the namespace, the selector, the label, and then if there are any annotations, the replicas, and then the status of the pods in the replica set, the template of the pod, everything is mentioned here. So now to delete replica sets, we can use the command kubectl delete rs or replica sets followed by the name. And the replica set is deleted. So that's all about replica sets. We'll see you in the next lecture. The next component is deployment. Deployments are a higher level of abstraction in Kubernetes that can manage replica sets and provide additional functionality for managing updates and rollbacks. They're responsible for ensuring that a desired number of replicas of a specific pod template are running and managing updates to the pod template. So one of the key features of deployments is that they can also, like replica sets, perform rolling updates. So rolling updates will allow you to update your application without any downtime, and it allows you to roll out updates gradually to reduce the risk of downtime and to ensure a smooth transition for your users. It also provides the rollback functionality, which allows you to easily revert to a previous version of your application if an update is causing any issue in your application. This also provides a safety net for your updates and ensures that you can quickly and easily recover from any issue that may arise. Another important feature of deployments is they can scale their operations. You can scale the number of replicas of a deployment using Kubernetes scaling features. This allows you to increase or decrease the number of running instances of an application depending on the workload. Deployments can also be managed using Kubernetes controllers. Kubernetes controllers are responsible for ensuring that the desired number of replicas of a deployment are running. This means that if a replica set fails, the controller will automatically create a new one to replace it so that they can maintain the desired number of replicas. In addition to managing updates and rollbacks, deployments can also manage other type of updates, such as changes to environment variables or image tags. This makes deployment a powerful tool for managing the life cycle of your application in a Kubernetes cluster. So in summary, deployments are a higher level of abstraction in Kubernetes that manages replica sets and provides additional functionality for managing updates and rollbacks. It allows us to perform rolling updates and rollbacks, scale the number of replicas, and manage other type of updates to your application. They can be managed using Kubernetes controllers and are very essential for managing the lifecycle of your application in a cluster. And deployments also ensure the high availability of the application through its scaling features. In this demo video, we will look at how we can implement deployments in Kubernetes. So in the previous demo, we saw about replica sets, but replica sets ensures that a specific number of pods replicas are running at a given time. But a deployment at a higher level manages these replica sets and provides declarative updates to pods along with a lot of other features. So let's see how we can create deployments on Kubernetes. As usual, we start with API version. And similar to replica sets, it is apps/v1. Then kind is deployment. Metadata, we give the name, demo deploy, and labels. And then we go to spec. Under the spec, we mentioned the replicas. Similar selector, we use match labels, and there we give the label for the pods. And once you have that, we use the template for the pod. Metadata, we give the labels, the spec, containers, image, nginx, also nginx, port, opening a container 8. So this is all about the deployment definition file. Let's go to the terminal and apply it. Now let's create the deployment. Kubectl apply chef deploy.yaml. And you see that the deployment is created. Let's see the deployment. So ready is 3 by 3, which means we have all the pods in the deployment up and running. Let's check the pods. So each of those pods are assigned an automatic name by the deployment, and each of the pods is hosting the nginx container. If you want to look at the details of the deployment that you've created, you can use kubectl describe deploy demo deploy, and it will fetch you all the details around that deployment. So the name is demo deploy, namespace is default, label app nginx, selector is also app nginx for the pods, and the replicas 3 is desired, 3 has been updated, and total is 3, and the available number of pods is also 3. And the strategy type here is rolling update. So rolling update means that whenever you create an update for this deployment, it moves out in a rolling fashion where each of these replicas will go down and the new updated replica will come up instead of the one which went down. So the similar pattern is repeated until all the replicas are having the newly updated application. And here is a pod template. And you can also see the events, whatever has happened inside that deployment. Also, if you want to look at the logs of each of these deployment, you can check the logs of the pods, kubectl logs and the pod name. There you'll see all the logs inside that pod. In this lecture, we will cover the update and rollback features of Kubernetes. Updates are an essential part of managing the lifecycle of an application in Kubernetes cluster. So deployments provide the functionality for managing updates to the pod template, allowing you to roll out new version of your application without downtime. One of the key features of deployments is their ability to perform rolling updates. A rolling update allows you to update your application without downtime by creating a new replica set. It allows you to roll out updates gradually and reduces the risk of downtime and ensures a smooth transition. The rolling update is performed by changing the pod template of the deployment. And deployments also provide several strategies for performing rolling updates. The most common strategy is the rolling update strategy, which updates the deployment one replica set at a time. So it waits for each replica set to become ready before moving on to the next one. This strategy ensures that the updated version of the application is available at all times during the update process. Another strategy for performing update is the recreate strategy. Recreate strategy deletes all existing replica sets and creates new one with the updated version. This strategy can be faster than the rolling update strategy, but it will induce some downtime during the updation process. Rollbacks are another important feature of deployments. If an update causes issues with your application, you can easily roll back to a previous version of the application using the built-in rollback functionality. The rollback is performed by changing the pod template of the deployment back to the previous version. Deployments keep a record of previous replica sets and can roll back to a previous version by creating a new replica set with the previous pod template and gradually replace the new replica set with the old one. This process is similar to the rolling update, but in reverse. So in summary, updates and rollbacks are features of deployments which manages the lifecycle of the application in a cluster. Rolling updates allow you to update your application without downtime, while rollbacks provide a safety net for your updates, allowing you to easily come back to a previous version of your application in case an update causes any issue. And deployments also provide several strategies for performing rolling updates and can perform rollbacks by creating new replica set with the previous pod template. In this demo video, we will look at how we can implement update and rollback features in Kubernetes deployments. Currently, we have the existing deployment. So we are going to update what we have right now. The first thing, what I'm going to do is I will change the image of this deployment. So for that, I can use a command kubectl set image deployment dot v1 dot amps slash the name of the deployment, which is demo deploy nginx equals nginx 1.16.1. And you see that the image of this deployment is updated. Let's check it. So if you look here, the container named nginx now has an image nginx 1.16.1. Alternatively, you can also edit the deployment using kubectl edit deploy followed by the deployment name. So here is the YAML file for the deployment, and let's change the replicas to 10. And it is edited. So Now let's see what is the change. So from 3, it has scaled up to 10 replicas. So this is how you can scale deployments, or alternatively, you can use kubectl scale deployment / demo deploy, and replicas equals 3. Now this will scale down. So whatever number you mention on the replicas, it will scale accordingly. If you look here, it has scaled down from 10 to 3. So now we made a lot of changes in these deployments. What if some of the change got us into a mess? That is where we use a rollout and rollback of deployments. So for that, let's check the rollout history using the kubectl command, kubectl rollout history deployment demo deploy. So there has been 2 revisions that we have made. So we can roll back to a previous version, and we can also mention the revision as well. So first let's roll back using kubectl rollout undo deployment deploy. So this will roll back to the previous deployment. This means that from Nginx 1.16.1, it rolled back to the image Nginx. And similarly, even if we make as many changes in these deployments, we can go back to a specific revision by using kubectl rollout undo to revision equals 2. Now it's rolled back, and let's see that now it's rolled back to the second revision. So the first revision was having the Nginx image, which we mentioned while we created the deployment, and then the second revision was when we changed the image of the deployment to Nginx 1.16.1. So we can roll back to any of the rollouts that we have made, and we can also see the history of the rollouts using this command. So that's all about this demo. We'll see you in the next one. Now let's look at how networking in Kubernetes work. The networking at a high level on Kubernetes provides a flat network for each of the pods across multiple hosts which is deployed on. And each of these pods has their own IP address, and that is used to communicate with other pods in the very same service. And these services provide load balancing and access control for these pods. Kubernetes also support network plugins for integrating different networking solutions to the cluster. And it also provides several security features such as network policies, which makes sure that only authorized traffic is allowed to flow within the cluster. Let's start with pod networking. In Kubernetes, a pod is the smallest deployable unit that can be created or managed. The pod can contain one or more containers, which shares the same network namespace and can communicate with each other using the localhost interface. However, pods on different nodes or in different namespaces cannot communicate with each other by default. So here also, if you look in the diagram, each of these pod has its own IP address. This is a pod 1, which has an IP 10.0.0.1, and then the second pod with 10.0.0.2, and then the third pod with 10.0.0.3, 10.0.0.0. So here is the node which has an IP address of 192.168.0.0. So to enable the communication between these pods, Kubernetes provides a networking model where each pod is assigned a unique IP address, as you see here. And this is achieved using Container Network Interface plugin, CNI. And this creates a virtual network interface on each node and assigns a unique IP address to each of the pods. So this will allow the pods to communicate with each other regardless of which node they're running on. Now let's talk about node networking. In Kubernetes, a node is a physical or a virtual machine that runs on the Kubernetes software and is used to host the pods, as you see in the diagram. Each node is assigned a unique IP address, as you see here, 192.168.1.1. And in the second node, we have 192.168.1.2. And these IP addresses are used to identify which node it is. And these nodes also have their own network interface, which is used to communicate with other nodes and external resources. So to enable communication between the nodes, Kubernetes uses a networking solution known as pod network overlay. And this involves creating virtual network overlay on top of the physical network infrastructure, which allows the pods to communicate with each other regardless of the nodes they are working on. For example, if you look in the diagram here, we have 10.168.0.1 as the IP address of one pod, and the same IP address is on another node. So here we have two different nodes, but the IP address is the same. If they are working standalone, the communication will happen within the node individually for each of these nodes. But if both of these nodes have to be communicated together, in that case, it will not work. That is because there is a conflict between the IP addresses in the pod. So in this case, we will have to use a NAT or a network address translator in order to map the IP addresses. But Kubernetes provides a facility to enable communication of pods without using NAT. Similarly, nodes can also communicate to pods without using NAT. How do we solve this? That is where we use CNI provider plugins. So what is a CNI? It's a container network interface, as we discussed earlier. And CNI is a flexible networking solution that creates an overlay across all the pods and all the nodes so that all these IP conflicts are resolved. It also offers IP management, DNS resolution, load balancing, and also isolation. And it also supports bridge, overlay, and direct attachment models. And it enables it to work with VLANs or IPsec, etc. And these plugins basically use JSON for container network configuration, and it is also easily integrated with Kubernetes. So some of the common solution providers are Calico, Flannel, and ViewNet. So for example, Calico is a networking solution that provides scalable high-performance networking for Kubernetes. It uses BGP routing to distribute routes for efficient routing and fast failover. It also includes built-in security features such as network policy enforcement, distributed denial of service protection, etc. And Flannel is another popular networking solution for Kubernetes, which is a simple and lightweight solution that uses virtual network interface to create a network overlay between the nodes. And it also supports a variety of network backends including UDP, VXLAN, and host gateway, and allows to work with a wide range of network topologies. So when do we install a network plugin solution? After we install the Kubernetes cluster, we install the network solutions. So that's all about this lecture. We'll see you in the next one. Now let's learn about Kubernetes services. What is a Kubernetes service? In simple terms, it's an abstraction that defines a logical set of pods and a policy for accessing them. It exposes the applications running on the pods as a network service. It provides a stable endpoint for accessing a group of pods, even as pods are created, scaled, or even replaced. And the services enable inter-pod communication and external access to application running within a Kubernetes cluster. And these pods are only reachable within the cluster network, so they can't be accessed externally without these services. That is where we use services to expose whatever is hosted on the pods. And the services offer a fixed IP and a DNS name for a group of pods which enables the external access. A service YAML manifest will identify which are the pods that is being targeted and what is the port which is being exposed and its type. A service also generates a virtual IP and a DNS for its targeted pods as mentioned. When the client requests the service IP, the port is load balanced across the target pods. And basically Kubernetes has three types of services: node port, cluster IP, and load balancer. Let's look at how services work with a YAML file. So here we have a pod template, which means we are hosting a busybox container on a pod named pod name with a label app my app. What we are going to do here is we are going to expose this pod externally. That is where we use a service. So in the service, API version, kind, metadata, and spec remains the same. And in the metadata of the service, we give the name service name. And in the spec, we have the type of the service. So here in this example, we are using a node port. And how does the service know which pod is to be exposed? That is where we use selector. So in the selector, we use app my app as the label. So what the service does is it looks for this selector in the pod labels, and whichever pod is matching the label, it will automatically be targeted. And in the port section, we give the port, the target port of the pod, and the node port. We'll look at node port in the upcoming lectures, but at a high level overview, this is how services work. Now let's take a look at node port service. A node port service is the simplest way to expose a service externally. It opens a specific port on every node in the cluster, and any traffic received on that port is forwarded to that respective service. This allows external clients to access the service using the IP address of any node along with the specified node port. Let's start by understanding what a node port service is. A node port service is a type of service that allows you to expose an application running inside the cluster to the outside world. So it does this by opening a specific port on every node in the cluster and forwarding the traffic received on that port to the corresponding service. And these node port services are primarily used when you need to provide external access to your applications, especially when you're using a development or testing environment. It allows clients to access the service using the IP address of any node in the cluster along with the specified node port. Let's explore how node port services work. When you create a node port service, Kubernetes automatically assigns a port from a predefined range, usually between 30,000 to 32,767. And this assigned port will be the same on every node on the cluster. So the traffic received on this port is then forwarded to the service. To understand this process, let's consider an example. Suppose you have a node port service defined with a target port of 80, and the node port assigned is 30,007. When a request is made to port number 30,007, Kubernetes will forward the traffic to the service, and the service will then route the traffic to the pod associated with it. And that is based on the load balancing rules. It is important to note that node port services rely on the cluster IP service for inter-pod communication within the cluster. The cluster IP service acts as an intermediary, directing the traffic between the external facing node port service and the individual pods associated with it. When creating a node port service, you can have flexibility in choosing the target port. It can be any valid port number such as 80 or 443 if you want HTTPS. However, The node port assigned by the Kubernetes must be within the predefined range of 30,000 to 32,767. And it should be available across all nodes in the cluster. The node port services offer a convenient way to expose your applications during development and testing phases. However, in production environments, it is common to use other service types such as load balancer or ingress, which provides more advanced feature for external access. So to summarize, node port services in Kubernetes enable external access to the applications running within the cluster. They open a specific port on every node and forward the traffic to the corresponding service. The node port services are often used during development and testing and rely on the cluster IP service for inter-pod communication. Let's see how node port works with a YAML file. So this is the YAML file for a node port service. You have the API version, kind, metadata, and spec. Kind is service. The name of the service is service name. And in the type, we have specified node port. In the selector, we have app, my app. So the service is going to look at the label app, my app for which pod or deployment it has mentioned. And in the ports, we mention the node port. We have a port which is open for the service, and there's a target port where we are targeting the pod or the deployment. And in the node port, we assign anything between 30,000 to 32,767. So this is at a high level overview on how node port with YAML works. Now let's take a look at the cluster IP service. So a cluster IP service exposes the service on an internal IP address which is only reachable from within the cluster. It enables communication between different parts of your application within the cluster. And the cluster's IP services are typically used for internal microservice communication. Let's begin by understanding what the service is. In Kubernetes, it is a type of service that exposes the application internally within the cluster. It provides a stable IP address that other services or pods can use to access the application. And this enables inter-pod communication. The primary purpose of a cluster IP service is to enable communication between different parts of your application within the cluster. It acts as an intermediary, allowing the services or pods to discover and connect to each other without having to know the specific IP address or the endpoints of individual pods. When you create a cluster IP service, Kubernetes assigns a virtual IP or the cluster IP to the service. This IP address is only reachable from within the cluster, and it cannot be accessed from outside. So this cluster IP service acts as an internal load balancer, distributing the traffic among the pods associated with it based on the load balancing rules. To show you how services work, consider an example where you have multiple pods running an application and you want them to communicate with each other. So by creating a cluster IP service and associating it with the pods, you can provide a stable IP address that other services or pods can use to reach to this application. This way, the service acts as a single point of contact for internal communication. So cluster IP services use the kubeproxy component, which runs on each node on the cluster to handle the routing and load balancing of traffic to the pods associated with the service. Kubeproxy will ensure that the requests made to the cluster IP are properly distributed among the pods, and it maintains the high availability and efficient resource utilization. One of the benefits of cluster IP service is that they automatically handle service discovery within the cluster. Other services or pods can simply use the cluster IP and service name to access the application, and Kubernetes takes care of directing the traffic to appropriate pods. It is also important to note that cluster IP services are internal to the cluster and not accessible from outside. If you need to expose your application externally, you can combine a cluster IP service with other service types like node port or load balancer. Let's see how cluster IP works in a YAML file. So here we have the same format, the service, and the service name is cluster IP name. In the spec, we have the type of the service, which is cluster IP. So even if we don't mention any type, by default, it chooses cluster IP as the default service type. And then the selector app, my app, and the ports, we have a target port and the port of the service. So that's all about this lecture. In the next lecture, we'll look at how load balancing service works on Kubernetes. A load balancer service is a more advanced option for exposing a service externally. It provisions an external load balancer in the cloud infrastructure that distributes incoming traffic across multiple nodes running the service. This type of service is useful when you need to balance traffic load and provide external access to your service, such as for web applications or APIs. When using a load balancer service, the cloud provider automatically assigns an external IP to the load balancer, and the traffic is distributed to the service endpoint behind the scenes. This allows clients from outside the cluster to access the service without needing to know about the underlying nodes or their IP address. It is also important to note that while node port and load balancer services allow external access, they rely on cluster IP service for inter-pod communication within the cluster. The cluster IP service acts as an intermediary, directing traffic between the external facing service and the individual pods associated with it. So in the load balancer service, it provisions a load balancer in the cloud infrastructure, and it acts as an entry point for the external clients to access the application. What is the primary purpose of a load balancer service? It is to provide external access to the application and distribute the traffic load across multiple pods or nodes. This type of service is used for web applications or APIs or any service that requires scalable and highly available external access. When you create a load balancer service, Kubernetes communicates with the underlying cloud provider to provision an external load balancer. The load balancer receives incoming traffic from the external clients and then distributes it to the pods associated with the service based on defined load balancing rules such as round robin or least connections. One of the main advantages of load balancer service is that they provide a stable external IP address that the clients can use to access the application. This IP address is assigned to the load balancer created by the cloud provider, and traffic is seamlessly routed to the backend pods running the service, ensuring high availability and scalability. Load balancer services are particularly beneficial when you require automatic traffic distribution, high availability, scalability without the need of manual configuration. The cloud provider takes care of managing and scaling the load balancer infrastructure and allows you to focus on your application. And it is also important to understand that load balancer may incur additional cost as the underlying load balancer is provisioned and managed by the cloud provider. The exact implementation and features of load balancer services can vary across cloud providers, but the core functionality remains the same. Let's look at how load balancer works with a YAML file. Let's take a look at how the load balancer YAML file works. We have the API version, kind, metadata spec, and in the spec we mention the type load balancer. The selector we give the label of the application or the deployment that we want, and under the ports we mention the protocol. It can be TCP, UDP, anything. And in the port, we open the port for the service, and in the target port, we open the port for the target. So here it is 9376. So the port of the service is 80 and the target port is 9376. In this demo video, we will look at each of the Kubernetes services, node port, cluster IP, and load balancer, how they can be implemented on Kubernetes. So in this demo, we have a deployment file, a deployment named demo deploy with a label app nginx, and it is going to run an nginx image. So I am going to expose this deployment using all of these services. Before that, let's create this deployment. The deployment is created. And you see all 3 pods for this deployment is available. Now let's create a service. So there are 2 different ways. Either you can use a YAML file, or you can also use a kubectl command to expose the deployment. The command is kubectl expose deployment, and the deployment name demo deploy, followed by the name of the service, let's say demo service, and the port, which is 80. So first we will look at the cluster IP type. So by default, Kubernetes uses cluster IP type of service as the default. So the service is exposed. It will get services. And you see that the cluster IP demo service is created. Now let's check if we are able to access the service internally. How do we do that? For that, since the communication happens within the cluster, we need to create another machine inside the cluster so that through that machine, we will be able to access this service. For that, I'm going to create a new pod. Kubectl run nginx image nginx. So I'm creating a pod named nginx, and through the pod nginx, I'm going to access the service. For that, we can use the command kubectl exec-it for interaction, and then the pod name nginx double dash. After double dash, we give the command that we want to run inside the pod. So here we want to run the curl command, curl http. Let's copy the cluster IP and the port 80. Once we run this, we see the content inside this deployment. So the deployment was exposed by the service, and the content is retrieved through a pod that we created additionally. So this is basically how cluster IP works. Now let's look at how node port service work. Let's list the services. We have our demo service with a cluster IP. So what I'm going to do is I'm going to edit the demo service from cluster IP to a node port. For that, I can use kubectl edit service and the service name. And here we have the service YAML file. And in the port, I'm going to add a node port to it. And I'm going to give 30,007. It should be between the values 30,000 and 32,767. And the type from cluster IP, I'm going to change it to node port. So once I save it, let's see the service. Now it shows the node port service. So the service has been changed, and let's check this service through the node port. So let's test this node port service by port forwarding. So once we run the port forwarding, it will run on the local host, and we can preview it here on this port 8081. And you see that the nginx page is being displayed. This means that we are able to access the service, and the service is working fine. Once that port forwarding is closed, you will not be able to access the service again. And this is mainly used during testing purposes in the development or staging environments. Now let's look at the load balancer. Currently we have the node port service. Let's keep that and let's use the kubectl command for the load balancer. Let's look at the deployment first. Demo deploy. So what I'm going to do is I'm going to expose demo deploy, and my name is load balancer, and the type is load balancer. The port is 80. The target port is also 80. And the service is exposed. Let's look at the service. So a new service called load balancer is created of the type load balancer. It has a cluster IP, and if you look at the external IP, it is pending, which means the cloud provider is assigning an external IP for this load balancer. Let's wait until the service is assigned an external IP. It might take around a minute, but keep on checking until we get the external IP. So here we have the external IP. Let's go and paste it and see what we are getting. And again, it is hosting the Nginx website, and we got it through this IP address. So this is how load balancer service works on Kubernetes. So that is all about services at a high level overview. In this lecture, we will cover the basics of microservices architecture, its characteristics, and how it differs from traditional monolithic architecture. So what is a microservice architecture? It is an architectural style that structures an application as a collection of small autonomous services, each running on its own process and communicating with each other using lightweight mechanisms. Each service is designed to perform a specific business function and can be developed, deployed, and scaled independently of other services in the application. The key characteristic of microservice architecture is that it promotes modularity and independence. Each service is designed to be a standalone component, which means if this service fails, the other two services will still be up and running. This is in contrast to monolithic architecture, where the entire application is built tightly coupled as a single unit. Another key characteristic of microservice is that it enables continuous delivery and continuous deployment. Because each service is developed and deployed independently, it is easier to release updates and new features to the application without affecting the entire system. This allows for faster development cycles and the ability to respond to changing business needs more quickly. One of the challenges of microservice architecture is managing the communication between services. Since each service runs independently, they need to communicate with each other through lightweight mechanisms such as RESTful APIs or message queues. Additionally, each service needs to handle its own data storage and processing, which can lead to complex data management. To address all these challenges, it is important to design services that are loosely coupled and have well-defined interfaces. This makes it easier to manage communication between services and maintain a separation of concerns. So in summary, microservices architecture is a style that structures the application as a collection of small autonomous services, and each running on its own process and communicating with each other through lightweight mechanisms. It promotes modularity, independence, and continuous delivery and deployment. However, it also presents challenges in managing communication between services and data management. That is all about microservice architecture. In this demo, we will look at deploying applications on Kubernetes using deployments. So for this demo, I'm specifically going to the Kubernetes repository where we have a lot of examples, and I'm going to choose the guest book. So I've cloned this repository and let's go inside it. And I'm going to use guestbook application. If we look at the components, we have a front-end deployment.yaml, front-end service.yaml, Redis master deployment.yaml, Redis master service, Redis replica, and Redis replica service. Let's examine each of these files in detail. So here we have a guestbook folder. And when we look inside the guestbook folder, we see that there's a front-end development.yaml file. Let's inspect that file in detail. So API version apps v1, kind is deployment. Metadata, the name of the deployment is frontend. And in the spec, we have the labels app guestbook and tier frontend, which is passed to the pod template here. And the replicas are 3. And we have the container PHP Redis, and we have used an image from Google Container Registry. And we also have resource request at CPU 100M and memory 100 megabytes. And then we also have an environment variable get host from, which is given the value DNS, and we have the container port 80 open for the deployment. So here we have the front-end service.yaml, which exposes this deployment that we have created, and let's see how that is done. So we have API version, kind, services frontend, and in the labels we have app guestbook and tier frontend. And here we have the labels app guestbook and tier frontend, which you can also observe in the deployment. So that deployment is getting exposed, and the type is of node port, and the port is open to be 80, and the selector is also mentioned. Now this is all about the front end. Now we have a Redis master deployment for a Redis master node, and we are using the image for the Redis and a service that exposes Redis at port 6379. And then we also have a Redis replica deployment, which creates 2 more replicas for the master and another service for the same. Let's go back to the terminal and let's apply each of these files. So this is going to create all the resources inside the guestbook application. So you can see that the deployment front end is created, the service front end is created, Redis master is created, the service for Redis master is created, and for Redis replica, the deployment and service are also created. Let's check if they have been created or not. Let's check the pods first. And you see that almost everything is now up and running. Some of those might take some time, but if you look here, the front end, all these pods as part of the deployment is running. The Redis master is getting created. Redis replica, one of the replicas has been running, and the other one is getting created. Now everything is up and running. If you want to check the deployments, you can also check kubectl git deploy, and you will see that the front end deployment, which has 3 replicas, are all created, and there is a Redis master deployment and there is a Redis replica deployment. Now let's also observe what are the services available. So if you look here, we have the front end service, which is of type node port and with a cluster IP, and then opening the port 80 and 32452. and there is a Kubernetes service which exposes the Kubernetes, and there is a Redis master service which is of type cluster IP, if you might have observed, or if you might remember that we use cluster IP for mostly for internal cluster communication. So here, if you want to check the front end, we can port forward using the kubectl port forward command for this node port service. Now the port forwarding has happened, and we can check the local host to preview the application. So the application front end is now served. Let's give hello world, and this will be written here. So this means that the application is working. We close it, let's try it again, and you see that you are not able to connect to the application. So let's change the type of the service from node port to a load balancer. So for that, I'm going to kubectl edit service frontend. I've edited the front end. Now let's check the service. The service is getting updated, and if you look here, the external IP has gone from none to pending, which means an external IP is currently getting assigned, and it will take some time for the external IP to be assigned to this front end service. Let's check again, and we have an external IP. Let's copy this and let's paste it here. And now we are able to access the application. So this is how we deploy an end-to-end application on Kubernetes. In this lecture, we will look at the basics of GKE, or Google Kubernetes Engine, how it can be used to deploy and manage containerized applications. So what is GKE? It is a fully managed container orchestration platform that allows you to manage, deploy, and scale containerized applications using Kubernetes. It is built on top of Google's infrastructure and provides a highly available, scalable, and secure environment for running your applications. At the core, GKE consists of a cluster of nodes, which are virtual machines that runs on Kubernetes softwares. These nodes are managed by GKE and can be automatically scaled up or down based on the need of your application. GKE also provides a number of additional features that makes it easier to manage your Kubernetes cluster. For example, it includes a load balancer that can distribute traffic across your application, a container registry for storing and managing your container images, and integration with other Google Cloud services such as cloud logging or monitoring. One of the key benefits of GKE is its ease of use. Because it is a fully managed service, Google takes care of much of the heavy lifting associated with managing a Kubernetes cluster. This includes tasks such as provisioning and managing nodes, scaling the cluster, and upgrading the Kubernetes software. Another benefit of GKE is its scalability. Because it is built on top of Google's infrastructure, it can easily handle large-scale deployments and provide high availability for your applications. Additionally, GKE can automatically scale your nodes based on the resource demands of your application, and that ensures that you have always the enough capacity to handle the traffic. So to use GKE, you need to create a Kubernetes cluster. This can be done using GKE console or the gcloud command line tool. Once your cluster is up and running, you can deploy your application using Kubernetes manifest, which defines the desired state of your application. In this demo, we will look at how we can create a Kubernetes cluster on Google Cloud. Let's go to Kubernetes Engine and go to clusters. If you are using the service for the first time, you need to enable the API, Kubernetes Engine API, and you have to enable it for your project in order to use it. Once the API is enabled, you will see the dashboard for Google Kubernetes Engine. And to create a cluster, click on Create. By default, Google offers two types of clusters, either autopilot, where Google manages your cluster, and standard, where you can manage your own cluster. So for the time being, I'm going to go for autopilot. So here we can give the name, the region, and then the network, the subnet, and then we can choose whether we want to have a public cluster or a private cluster. And then we can decide the pod address range, the service address range, and then the release channel on how we want to update Kubernetes versions and automation. We want to enable Anthos service mesh. We want to enable any security features like RBAC, binary authorization, and secrets, and also some metadata if we want to add. After that, we will see all the details here, and we can create the cluster. And the cluster will get ready to be spin up. Now, if you look at the standard cluster, you can mention the name, the location type, the zone, and if you want to specify the node locations, then you can specify where you want to have the nodes, and then how you want to upgrade Kubernetes and what version should it have. And you will also see the cost changing according to your requirements. And here's the node pool. Here by default, there is a pool with 3 nodes. And if you want to enable cluster autoscaler, you can check this box. Again, if you want to specify the node location, you can do it. And then node pool upgrade strategy, either if you want a surge upgrade or a blue-green upgrade. And then here on the nodes, you can configure the node settings. What is the type of the image that you want? Then the machine type that you want. Google offers all these variety of machine families: general purpose, compute optimized, memory optimized, and the cost will also change accordingly. You look here, it is $110,000 for M2 MegaMem 416 machine. We go for a general purpose. Let's go for an E2 micro. And if you look at the cost, it is $121. And the balanced persistent disk is what we are choosing as a boot disk. We can choose either standard, SSD, or balanced. And we can also choose the size of the boot disk. Here I'm going to choose only 10. Initially it was $121, but now it has reduced to $94. And then you want to choose how you want to enable the encryption on the boot disk. And also, for a discounted purpose, you can use spot VMs if you are not using any stateful applications, because spot VMs, after a day, like preemptible VMs, it will terminate by itself and gets spin up again. If you enable it, you will get further discounts. And the money has become $81. And then on the networking, you can mention the networking side for the node. And security, you can choose the service account, the access scope. And in the metadata, you can add labels, stains. And for the cluster, you can have the automation part. You can enable notifications if you want to autoscale, either if you want to provision any nodes or if you want to vertically autoscale the pods, and how you want to autoscale either by utilization or by balancing it. And in the networking, you can choose which network the cluster want to be deployed on, which subnet it want to be deployed on. And then you can choose private or a public cluster. And you also have other networking options here: data plane, Calico Kubernetes network policy. And you can also choose the DNS provider either as Cube DNS or Cloud DNS. And the security, you can enable binary authorization or shielded GKE nodes, confidential GKE nodes, workload identity. Workload identity is basically the service accounts that you're using inside the cluster that you can apply IAM roles with, and RBAC for role-based access control, and also legacy security options like legacy authorization or a client certificate. And metadata is similar, and any extra features if you want to enable Cloud Run for Anthos, you want to enable Anthos Service Mesh, Cloud TPU, backup for GKE, These are the additional features offered by Google for productivity. So that's all about the standard cluster. It takes approximately 5 minutes for the cluster to be spin up, and it is also the fastest in the market. Even if you compare other cloud providers, AWS takes around 15 minutes, Azure also takes around 10 minutes or more, but Google Cloud spins up Kubernetes clusters at the fastest rate, and that is less than 5 minutes. So let's wait for the cluster to be provisioned. In the meantime, we can also look at other functionalities provided by Kubernetes engine. Here it is workloads. Workloads are basically loads that you're running inside the cluster. Any workloads that you're running inside the cluster will be shown here. The services and ingress that you are going to run, any applications, secrets or config maps, then storage, anything that you want to create related to the Kubernetes engine, it can all be accessed through the console as well. And there is backup for GKE, which acts as a backup for your GKE cluster. And let's go back to the clusters. Now the cluster is now ready. So how can we connect to this cluster? You click on the three dots, you'll see the connect option. And here there is a command line which you can run in the Cloud Shell of Google Cloud, and the Cloud Shell will be provisioned, and there you can enter and use it as a CLI. Once you hit enter, and now you are inside the cluster. Now you can run kubectl get pods. You look here, no resources were found in the default namespace, and that is because we haven't deployed any workloads in here. Now let's look at the Kubernetes workloads by adding kube system namespace. So if you look here, within the kube system namespace, we have all these pods running, and these are all deployed as part of Kubernetes while setting it up. So whatever workloads that is run by Kubernetes is under the namespace kube system. So I can show you on the workloads. You can deploy an application or you can show the system workloads. So here you can select the namespace as you wish. And here are the workloads that is running in the namespace kube system. You will see the status, the type, daemon set, deployment, and the namespace, the number of pods, and the cluster where it is running. So this is basically an overview of Google Kubernetes engine.
Hello and congratulations on completing this course. I hope this course has helped you gain a solid foundation on the key concepts, terminology, and the technologies behind Kubernetes. Throughout the course, we started with the introduction to Kubernetes and then to the Kubernetes architecture, its components, Kubernetes components like pods, services, replica sets, deployments, and we also looked at deploying applications on Kubernetes. We also discussed about the microservices architecture and how Kubernetes works on cloud, specifically on GKE. Once again, congratulations on completing this course, and I wish you all the best for your future endeavors.